So now we're looking at systems of linear equations. This is the next step in being able to solve optimization problems, because when we eventually get to optimization problems, what we're going to have is we're going to have these things called constraints. And the constraints are basically things that need to be true for our situation. They're limits that we need to live under. And it's going to turn out that the optimal values that work for all of our constraints and that optimize our problem are going to happen at the corner points of these constraints, which means we need to find out where they meet at, or in other words, where the two equations are true at the same time. And so we're going to look at some techniques for finding those values. And that's what the goal of this portion of our lesson is about. So for starters, we got to talk about what it means to be a solution to a system of linear equations. So a system of linear equations, for what we're looking at anyhow, are going to be two equations with two unknowns in them. And a solution is going to be an ordered pair that works or that satisfies both of the equations at the same time. So it doesn't just work in one of them, but it works in both. That's important. So as we look at this, we can try to determine if negative 2, 2 is going to be a solution to this system up here. And so what I would do is I would first of all test it in the first equation. I'm going to use blue to talk about this one. That if I place negative 2, 2 in, I'm saying replace all the x's with negative 2 and replace all the y's with positive 2 and see if the equation is true or not. That's going to get us negative 14 minus 6 is negative 20. Negative 20 is negative 20. This does not necessarily mean negative 2, 2 is a solution. It means it works in the first equation. We also need to test the second equation. I'm going to use red ink to talk about this one. So if I replace the x with negative 2, and notice how I've done that. The original equation was negative x. I need to do negative of negative 2 plus 2 times the y value, which was 2, is supposed to equal 6. So in this one, negative negative 2 is positive 2. 2 times 2 is 4. 2 plus 4 is 6. So it looks like this one works as well, which means, yes, negative 2, 2 is in fact a solution because it does satisfy both equations. Let's go ahead and look at the second one. Let's see if the second one's also a solution. We're going to use the same thing. We're going to talk about this first one being blue. We have negative 6 times the x, which is negative 4, minus 4 times the y is supposed to equal 24. So we get 24 minus 0 is 24, or 24 equals 24. That checks out as well. Let's try the second equation. If I plug negative 4 in for his x value and 0 in for his y value, I get negative 28 plus 0 equals negative 20, or negative 28 equals negative 20. Those two things are not equal. Since negative 4, 0 was not a solution to both equations, it is not a solution to the system. In order to be a solution to the system, it's got to work in both. So if we think about what that means graphically, in this example that we're looking at right now, if I were to graph each of those lines, then negative 4, 0 would be a point that's on the blue line, but it's not a point on the red line, which means it's not a solution. But if we go back up and think about what's going on graphically for the first example that we looked at, then the ordered pair negative 2, 2 worked on the blue equation. Therefore, if we graphed it, it would be on the blue line. But similarly, negative 2, 2 would be on the red line as well. So the ordered pair that's on both the blue line and the red line would be the solution. So if we think about what that means graphically, it means where do your two lines cross at? That's the solution. So we can actually solve a system by graphing if we just graphed both of the equations, both of the lines, and saw where they met at. So if I start off with this blue guy here, his y-intercept is -1, and his slope is -2. So we go up to left 1, up to left 1, or down to right 1, or down to right 1. I would highly advise doing as many ordered pairs as will fit on your graph, because what we're looking for is going to be the intersection. So the more points you've plotted, the better off you're going to be, because if you're anything like me, your freehand lines aren't perfect. And so it's hard to see exactly where it's supposed to be going through. Let's go ahead and look at the other line. He's got a y-intercept of +2. A slope of -1/2 is saying down 1, right 2. But if I go that way, I'm getting further away from the blue line. So instead of continuing in that direction, we can think about it as going up 1, left 2. And right there we see where the intersection is, so we don't really need to go any further. Now, if you're being asked to solve a system of linear equations by graphing, the graph in and of itself is your work. It's not the answer. We can see in the work here where they cross at. But then to solve the system, we want to give this value of -2, 3. That's the ordered pair where they cross at. So that's the ordered pair that would be a solution to both equations at the same time. So what if you were trying to find the solution to a system, and when you graphed them, both lines end up being parallel to each other? Where do they cross at? Well, they don't. So it is possible to have a system of equations that has no solution. And so we can say no solution. We can use this empty set symbol as well. So this solving systems by graphing seems pretty sweet, doesn't it? It seems like it'll be pretty easy to get your solutions. It seems like we don't need to learn anything else about systems of linear equations. Sure would be nice if that were true. Let's take a look at this example here, and let's see what kind of problems we're going to run into. Well, this first guy's pretty easy to graph. He's got a y-intercept of 3. Slope of -2 says to go either up 2, left 1, or down 2, right 1. So we can do that a few times until we're off the graph. So far, so good. Doesn't seem too bad. Now let's look at the second line. Y-intercept of 2. Slope of +1/2, so up 1 over 2. Well, we can see that they definitely cross here. What value is that, though? It looks like it's about 1/3-ish and maybe 2.2-ish. But this is a problem. If you have to use ish in math, that's no good. So this is actually a problem in the graphing method. If you're using the graphing method and your solution is not at a nice, happy, integer ordered pair, then you really can't even get your answer. So that's a problem. So the graphing method is actually more of a method to get the basic understanding of what a solution is, what it means to solve a system, but it's actually not the best method for actually solving it unless they happen to meet at nice, happy, integer ordered pairs. So as we progress through the rest of the lesson, we're going to see how would we solve this system then? What would be some other more algebraic ways of doing it, where when we know that the answer needs to be a fraction, when we can find that actual fraction?